Hey kids, sorry that you have a second or two video lessons in a row. I was planning on being out today, but I did not plan on the snow day on Friday. Not that I'm complaining. Please note that your homework has one less problem than on your handout. I decided against number 5 as I looked it over. I just think it's overly, needlessly complicated. So go ahead and do it if you want, but you don't have to. 7, 9, and 10 is what I will be looking at. So I wrote this warm up more in the UMD style by asking you just to show me how you would get to this line integral instead of doing a curl. I also used this um, notation for S, right? The sigma, because I've seen UMD do it. So they are asking me to apply Stokes' theorem to show that if I asked you to do a curl, you didn't have to, you can do a line integral instead. So doing a line integral instead, hey, why is this negative here? Yes. The normal vectors are pointing in, right? So negates. Now, I could have just said, show that you do the curl to do a regular line without putting this notation there, because remember, this notation assumes counterclockwise. So if you're going to go clockwise, you need to have the negative there. So sometimes you have to realize that. But remember, Stokes lets you do a double integral, which is a surface integral, or let you do a line integral around the boundary. And this problem is asking us to set up the boundary line integral. So let's look at our boundary. I can see the surface. It's the green portion of the cone below the plane, z equals 6. So the boundary going in a clockwise direction looks like this, right? So let's find out the algebraic expression for that. The plane z equals 6 is equal to that cone. So I'm going to say 6 is equal to the square root of 9x squared plus 9y squared. I'm going to square both sides, divide by 9, and get 4 is equal to x squared plus y squared. Because if I'm doing the line integral, right, I need to incorporate the vector field and the boundary. So I take the vector field and shove the boundary into it, and then dot it with r prime. Right? So let's do that. So, and when honestly, I don't know that I would have chosen line integral looking if I was given the choice, right? Look how ew that is. So I'm going to go up to f, and I'm going to have sine of xy, but that means I need to parametrize my surface first. I'm sorry, my boundary first, right? But I have a circle with a radius of 4, so I have 2 cosine t, 2 sine t, and then because I'm doing the boundary, what is z? Ignore the surface, just do the brim. And then I can't dot that yet because I haven't incorporated the force field, but I do need to eventually dot with r prime. So that's negative 2 sine and 2 cosine. So now incorporate the vector field by putting this x, y, and z up into f. Oh, I forgot negative. So I have f, sorry, I have sine of x, 2 cosine t times 0. That's nice, isn't it? Because that's just 0. Then I have 2x cubed plus xy squared times 0, right? Then x squared cosine y times 0, so cosine of 0, but that's not 0. That's 1, right? Now dot it with r prime. And I get 0 times this is 0. I get 2 times this 2, which is 4, times 2 cubed, which is 8, cosine cubed t times this other cosine. Oh, that's cosine 4 to the 4th, right? And then I have this nonsense, but times 0. Which sure enough is negative line integral 32 cosine to the 4th t dt. Yay, I did it. Woohoo! All right, so let's go on to a couple more Stokes examples. Remember Stokes' theorem, it lets you choose. I can do a line integral, boundary, or a surface integral along the surface. So look at this one. Give you a moment to copy it down. And then look at your surface. Do you see what your surface is? Right, the plane z equals y. Oriented clockwise, viewed down from the z-axis. Think about what that means. And I have boundaries on x and y. But z is only in terms of y. So this, remember, tells me that if I'm going to do the surface integral, right, I'm going to have to negate it. So here's what the surface looks like. There's the plane, called it lowercase sigma this time, but again, UMD uses capital sigma. So here's the plane going clockwise around that. So can you see when they ask me to do the line integral? Can you see why I would not want to do that? Why would I not want to do a line integral? Right, look at that surface. And this is what number 5 was like. Number 5, you actually were given a cube, and you certainly do not want to do a line integral around the cube, but there's still multiple surfaces too, which is a little bit annoying. So that's why I said not to do it. And I did this example instead. So can you see that to do a line integral, I would need to do 4 separate line integrals? No thanks. I don't think I want to do that. So I want to do the curl instead. So they asked me to evaluate this, but I'm so stoked. I can do the surface integral instead, and that is a pretty simple surface, right? So instead of evaluating the line integral, I'm going to do the curl. Because z is in terms of actually not just a function x comma y, it's y only. I'm not going to do the actual dot n. I'm going to do that p, q, and r version, right? So I integrate, just like the boundary. When I'm doing the line integral, I have to involve the vector field by putting the parametrized version of the curve into the vector field. How I get the vector field into the problem here is by doing the curl of the components of the vector field. And I just wrote out what I got here. And then this is my P, Q, and R of the surface integral when I don't have to use, when I can avoid parametrics, right? Why is this negative out here? Right, the clockwise. So as soon as I use my P, Q, and R version, and remember this is the result of the dot product, right? That dot product when I have f in terms of, right, just 2 variables, and in this case only 1. But I'm going clockwise. So this is going to be negative. And once I do this, I'm now down to looking at the 2D surface, aren't I? And look at the 2D surface. It is just a rectangle. Going from what? 0 to 1 and 0 to 3. So what am I going to have here? The opposite of P, negative 2xy, times the partial of f. What's my f again? That's my z in terms of two variables, and in this case, again, only one. So, oh, that's nice, because what's the partial of the plane with respect to x? Oh, snap. Plus negative y squared, but what are you doing? Negating. So I have y squared times partial of f with respect to y. And then plus r. And I'm going to integrate that, dy dx, right? I'm going to integrate with respect to y first. Remember, that goes away. So I'm integrating y squared plus 4y cubed from 0 to 3 dy. And then you're going to integrate that result, dx, from 0 to 1. Don't forget the negative. Because the answer to the integral is 90, but the answer to our curl f dot n is negative 90, because I was going clockwise, which means when you're doing the surface integral, right, your normals are going to be pointing in. Cool. Let's do another one. So I've given you a picture of the shape. Let C be the closed curve oriented counterclockwise as seen from the top, right? As seen looking here, looking down here. I have a curve, right? So closed curve is your boundary. So this time they gave me the boundary. They're telling me I'm oriented counterclockwise. So that's a positive line integral. And it's formed of the intersection of the cylinder that is shifted slightly off of the origin with a radius of, with a radius equal to a fourth, and this hemisphere with a radius of 1, right? Apply Stokes' theorem to the integral, to the line integral. Ew, can you see why I don't want to do that? I don't, right? Parametrizing this, right? I can see kind of sort of my boundary there, and I am going counterclockwise, but ew. So applying Stokes' theorem to this integral means write the curl integral. Right? Oh, let's see, did I? Probably don't need to write this stuff. I probably typed it in. Oh, no, I didn't. Okay. So remember, that is the curl of f dot n ds. And then can we use our P, Q, and R? Right, of this? Oops, I don't know why I was doing that. We can, because, right, don't you have z by itself? So I'm going to, right, transform this into my version, my P, Q, and R version. So first I have to find my surface, though. So I do have to do a little setup work. So I have an intersection of this cylinder and this hemisphere. So check this out. Let's do our curl work first. And where is my vector field? Ah, here, right? So what am I going to get out of this? Do this computation, and I got 0 minus 0, which is my p. I got negative 1 minus 1, which is 0, right? That's my q. And then I got 0 plus 1, which is my r. So I'm going to anti-differentiate negative 0, partial, don't really need the surface because, right, don't really care because I'm going to multiply by 0, and same here, and then I don't need a partial for here. So, haha, didn't really need you because of what my curl turned out to be, right? So I just have 1 dA, because when I do this, now I can look down on the 2D surface. And again, looking at this surface, down the z-axis, what do you see? Right? Don't you see, right? That image on the 2D is just a circle with a radius of what? A half, right? Because that's where this is intersecting this. So I don't actually need to integrate at all. Woot woot. All right, so I did one example where they said, do you want to do curl? In the warm-up, they gave curl and asked you to do, the surface integral with curl, but we did the line integral. Parametrizing was pretty easy. And then I did an example where we could have done they asked us to do a line integral but apply Stokes, and we realized the line integral would have been 4 problems, so we did the surface because it was a pretty nice surface. Then I did this problem where they asked me to do a line. I chose to do a curl of the surface, and it turned out, the integral of the curl of the surface, turned out I didn't actually have to integrate or need to write a function for the surface at all. So let's try this last one. I don't particularly like, and I haven't seen any UMD problems written like this, where they're saying C is the curve, right? So this is the boundary, oriented clockwise, but as seen from the origin. So that would be looking from normal land, right? If I'm looking down Z, that would be counterclockwise. I think that's slightly annoying. I will not do that. I have not seen University of Maryland do that. So they're asking me to evaluate the line integral, right? Again, I don't want to do the line integral. To parametrize the boundary around here would be a little bit devastating since it's the intersection. So I'm not going to do that. And instead, I'm going to apply Stokes and do the curl of the surface. So just like before, I'm going to do the curl first, right? Because maybe my curl turns out so nice that I only am integrating, just looking at the 2D image, and my integral is just a 1. That didn't happen this time. So I did end up integrating, right? When I do have a nice Z, but it is an intersection. So in order to find the partial of my surfaces, because I didn't end up with just a 1 here, I have 3y squared times the partial of that surface. Now I do have a 0 here, which is nice. And then I have plus z, right? But I need this, and I have to get rid of this. So here is the intersection. So like we did before, let's put them equal to each other. Or here's a handy little trick. Do you see that if I multiply both sides by 4 here, I get 4z is equal to x squared plus y squared? And then look at this. So can't I say that, I think I did type this, z is equal to 8 minus, I just copied that over. But now look at this. Do you see the 4z right here and right here? Then I isolated the radical, right? So I did z minus 8 is equal to negative square root of 4z, and then squared both sides. Then I did algebra, and I did pulled that 4z over and factored. And when I factored, I got 2 answers, of course, because that's a quadratic. But when I factored, I got z is equal to, or I'm sorry, my 2 factors, z minus 16 and z minus 4 is equal to 0, which means z is equal to 16 or 4. Can you see why 16 wouldn't work? Right, if you plug 16 back into there. Right, you can see that that is going to lead to negatives, right? So 4 is my answer, my only answer. So that's nice. If z is equal to 4, and that's my surface, what is the partial of the surface with respect to x? Oh, snap, that goes away. So yay, it did go away. But what is this z? 4. So I can just look at my 2D surface, can I? Love when that happens. Z is equal to 4, so I do have an integral of 1 dA. And what is the image? 2D image of that intersection? If z is equal to 4, what does that make this radius here, right? Woohoo! Right, because that's where it was intersecting, right? This plane z equals 4. Nice. So notice that I didn't really do a whole lot of integration, right? Which is very nice if I can do some problems, and the more you do, the more you realize, oh, I think this is going to go away. I kind of saw that in the first one. I didn't see that immediately with this one because I had these two surfaces that I needed to put equal to one another, so it wasn't immediately obvious I was going to get something so nice. But as soon as I had z as a constant, remember the last time we had z is equal to, was equal to just y in 1, some nice math happened with that. So if on an assessment, and that's why I think that some of the UMD problems, they ask you to just set up and not evaluate, because some of them maybe just are some nasty evaluations. And they just want to make sure that you can recognize and set up the going from line to curl, integral, and backwards. The homework problems tonight do ask you to evaluate, but they should be ones that are reasonable, which is why I took number 5 out, because I felt it was just not reasonable. Speaking of UMD, the substitute has the copies of the UMD. I think I said that at the beginning, but don't remember if I did or not. So he does have copies of your UMD set. It's not due until, look at the calendar, because I updated it with the snow day. I think I moved the test and moved when the UMD problems are due, but check it out. I don't have it up in front of me right now. All right, well, I will see you tomorrow, and have a great rest of your day.